Okay, good morning, good evening, good afternoon. Welcome for this 2-hour session where today we will discuss about the NoSQL database Apache Cassandra. I'm Cédric Lunven. I'm leading the developer advocacy team at DataStax. You have seen me a lot of time, multiple weeks. We are there 1 week over 2 doing those live. This is my coordinate, Twitter, LinkedIn, GitHub. I would be happy to have you in my network. Never hesitate to invite me. So I'm a certified Cassandra expert, trainer, speaker, Java geek, doing a lot of coding, building APIs, microservices, integration, and a lot in Spring lately, but not only. And today with me, we do have Peter. Hi, Peter.
Hi, Cédric. Salut. Welcome, everyone. Thanks for joining us. So I work with Cédric. I run San Francisco Java User Group. I work at DataStax to help developers succeed with Apache Cassandra, Stargate, Cassandra, all of our open source technologies. And a long-time Spring Framework person also from Elastic, number of other places, and very, very excited to be here today. Basically, former career app dev person and now turned database guy. So yes, as Cédric said, I'd love to have you in my network. Please find me on LinkedIn or Twitter. And let's get started. Thanks for having me today, Cédric.
Oh, pleasure is shared. We will have so much fun together. All right, okay, so a little bit of housekeeping. It's not only me and Peter on screen, as usual, help to prepare the content, that hosting the session, that answering the live. This is the distributed team across the world. Try to bring some diversity here and there. Okay, it's a live workshop. It's an interactive workshop. Never hesitate to ask questions either on the YouTube chat, but when the session ends, so does the chat. So we Discord room where you can ask a question all day long, and it's so Discord. The link should be in this description below. But we also have a robot in the YouTube chat that will help you with the links you will need today. So for instance, !GitHub will give you all the instruction. !Discord will give you the Discord link. Okay, I myself will play a little in the chat and give you a couple of commands, but Rex, Peter, and more could help you with that. So interactive, we will play game together, and in 2 minutes I will switch my screen to ask you question live. You will participate. I will ask you question and you will see your answer showing on my screen. We are live both on YouTube and Twitch, but Twitch is really just a backup. Really, we are mostly looking at YouTube and the chat for the question. It's a workshop, and we are proud to say not a webinar. We expect you to do the exercises with us because, hey, why not, you know? And you don't have nothing to install for that. All the instruction slides are on GitHub for you. You can download everything. And we will use Cassandra, NoSQL database, of course, and you don't have to install it either. We'll use a cloud product called ASTRA, which this is where Cassandra lives. Okay, and if we need to code a little bit, we tend to use Gitpod. For this very workshop, there is no code, so no Gitpod. We can skip that part. There is no just to attend this session on YouTube. But there is better. At the end of the session, we will give you an assignment, some homeworks, very easy, a very small form, 3 questions. And you were just showing us that you did the hands-on with us, and we will redeem you this nice badge that you can brag on LinkedIn or wherever you want with it. So pretty cool. Almost 600 people now having this badge. So stay tuned, stay up to the end, and we will explain you how to submit the form in the end. I told you about quick overview. Let's discuss all together, okay? Let me ask you at home a few questions. So to participate, you open a new tab or you use your phone. You scan the QR code or if you open a new tab, you go to menti.com and you enter the code on screen, 57881593. I told you about some commands, so let me do Menti just for you to copy paste the code from the YouTube chat. Okay, so I think I do a 3 question in the beginning, very fast, just to assess what is your level, what do you expect from the session, where are you from? There is no competition with these 3 first questions, but at the end of the session, again, we will play a game together with 5 or 6 questions. And this time, if you answer fast, you get more points, and the best among you will get some swag shipped to their location for free. So again, stay up to the end. So let's, how many people do we have? I see 31 with me right now on Menti, and on YouTube, we are 100 seconds. Come on, I could wait a couple more minutes, but not too long. We do have a full packed agenda. So let's have, let's say, half. I will wait up to 60 people with me with Menti. So again, open a new tab, menti.com, enter the code. And the code is at the top of my screen. The code has been provided to you in the YouTube chat, 57881593. Okay, I see it's not moving really anymore. So 56, 57. Okay, so again, in the beginning, no competition, so we can start and you can catch up. Okay, so the first question I do have for you today is, where are you from? Here is a map. Put your location in the map and let's see all together where people are dialing from or watching the YouTube live from. It cannot be more live than this, right? Okay, oh, look at that, distributed across the world, so both North America and India. I like always to say thank you for people in Asia to join. It's starting late for you, so we will try to stay on time. But sometimes we are just a bit longer.
Looks like a few folks from Brazil too.
Yeah, look at that. Europe as well. Okay, cool. See, it's live. And now we have 70 people with us on the Menti. Pretty cool. So almost everyone joined the Menti. So that's super cool. All right. Question number 2 is, okay. So for some reason, it was my only question. Yeah, pretty strange. I'm pretty sure I had that question, where are you from? You know, and what is the level in Cassandra? But never mind. Hey, that's the alia of the live. No big deal. Keep this window open at the end, and this time I'm sure. Look at this quiz. We will come back here at the end, and I will ask you a question, and if you answer fast, you get the points.
And bragging rights.
So yeah, not sure why I missed those 2 questions, but never mind. It's not a big deal. You understand how it works, how Menti works, so you will be fine at the end. So this is NoSQL, specialization. What is Apache Cassandra? How the distributed system works and the CAP theorem. Create your own partition with ASTRA, with Cassandra ASTRA, data modeling, and playing the game together. Peter is the guru today, will do mostly the talks, and I will be the hands-on. And I think now, without further ado, I will let Peter hang over, and I will just hiding in the back.
Awesome. Thank you. Thank you, Cedric. All right, let me share my screen. Okay. Is that coming through?
Let me see. Yeah, you are now sharing.
Cool.
You're the boss.
Awesome. Awesome. All right. Thanks again for having me. Yeah. So Just a super quick, a primer. Interesting. Cedric was presenting this at a recent She Loves Data conference over the weekend. I thought it was kind of interesting as a reminder about databases that they aren't in fact this monolithic architecture, right? Is that you can actually kind of split apart and look at the separate layers of, they have this interface, right? They have an execution engine and they all have, different storage engines. And I think looking at these three aspects is kind of important because with relational databases, it's really consistent. With NoSQL databases, there's a lot of different approaches to each of these three things. SQL is obviously pretty familiar to us here, but again, that has a lot of different implementations under the hood, right, across your different vendors, as same as your query planner, and then how is the storage actually accomplished? What is the storage interface, right? So, these really vary. Even within relational database vendors, right? But with NoSQL technology, it's really quite different across the board in a very different way. Relational databases, of course, obviously very versatile, right? I mean, you can use them for online transaction processing or online analytical processing alike, but they handle lots of transactions, lots of use cases. But there's a limit to these things. Once you get past a certain level and volume of data, how do you get a quick response time? How do you get, how do you get them to perform at low latency for your queries? Historically, the relational databases, as we all know, right, they were designed to run on a single machine. They came from this era where, we had single servers that we care and fed and kept alive, but now, in modern times, you have machines generating data. It's not just users, right? And with so many people and applications connected to the entire internet, the data volume is just going crazy. I don't know about you, but folks in the audience, just say in the chat, like, how many devices do you have, right? Besides your laptop at home, do you have a phone? Do you have a tablet? Do you have a watch? I mean, if you're like Cedric, you probably have a phone, a tablet, a watch, and then you have a backup watch, and then you have a secondary tablet, and then you also have a PC. So that's like, we're coming up on 3 or 4 devices per person here. So, with that kind of level of requirements, higher data volume, faster data, and different types and new types of data, it sort of mandated a new system. And that's kind of where NoSQL came in. It is important to note, however, though, that relational databases aren't, stuck in 2010, right? New SQL systems have the same SQL interface under the hood, but they're trying to figure out how to solve the distributed architecture problem, right? Like VaultDB or Cockroach. They try to address this sort of stuff through partitioning and sharding. And that can get hard, particularly to operate and troubleshoot. But what's interesting is that you got to be careful with that, right? Some of those approaches to new SQL clustering, they can change actually the nature of database integrity and how consistency is handled with a distributed ACID transaction. It's not like the simpler, more straightforward ACID behavior, right, on traditional non-clustered scenarios. Back 2010, this is a big problem, right, for all the web giants. They're starting to run into limits of relational approaches, and suddenly you start seeing NoSQL, meetups pop up everywhere. And I think over time, we all came to understand that it's not NoSQL, it's just not only SQL, right? So it's not the negation of SQL. It's just not only. And then, right around 2008, Avinash, Lakshman, and Prashant took the Dynamo paper and combined some of the Google BigQuery or Bigtable, concepts. And then that developed Cassandra. That was at Facebook, basically to power the inbox search feature. And then Facebook released it as an open source project in July 2008. So NoSQL was born to basically address, right, this sort of how do we scale out horizontally and not vertically, right, and over commodity hardware where data is replicated, and how do we handle a wider variety of modern data types. Now, sure, academically speaking, there's lots of more types than NoSQL databases than what you see here on the slide. But today, these are a lot of the sort of popular mainstream ones. I mean, you could argue that things like graph databases or maybe an object databases are maybe a little niche, but these are the mainstream ones. And I think personally, I like to think of NoSQL as just enough database for a specific developer's use case, right? Where you, the developer, you're matching the technology with the use case. Okay. So let's talk a little bit about, that's a little bit about why, NoSQL. Let's talk a little bit about Cassandra itself. We mentioned it originated at Facebook, and then later Apple, Netflix, other companies that also have just tons of data and users, but could not compromise on performance and availability, started getting involved in the project. So with Netflix, nearly all of its streaming data is stored in Cassandra. Hundreds and hundreds of clusters, 30 million ops per second on the most active single cluster. But that's just the most active single cluster. Like the overall count is significantly higher than that. Clusters are, of course, distributed all over the world using multiple data centers. And I mean, that's not even their biggest, that's not even the biggest deployment globally. Apple's scale is significantly higher. Now, this photo here from like a conference room is several years old. I think it's probably up closer to like maybe 200,000 dedicated Cassandra, servers. Apple remains one of Cassandra's biggest users and very active committers. Netflix contributed a lot of the ecosystem tooling, Spotify as well. And, they've been very active along with contributions from Spotify, Apple, and I think Instagram, right, Cedric? Or am I getting that wrong? Was Instagram also a contributor?
Yeah, at some point. Not sure that it's.
Yeah.
Yeah. Famous
I thought so.
Cassandra engineer working on Instagram. Yeah, for sure.
Cool. That's what. Okay, I wanted to make sure I got that right. Excellent. All right, thanks. So, what is it? Right. Enough preamble. Why are so many leading companies and disruptive technologies adopting this sort of thing? So let's start with the simple what it is, right? I mean, we already teed it up. This is a NoSQL distributed database. So we'll focus more on the distributed part here in a second. But each part of Cassandra, each instance of Cassandra is called a node, right? And this contains a full Cassandra database. Each node can handle roughly 2 to 4 terabytes of data and thousands of operations per second per core. And what's hard for so many databases is the ability to handle that level of volume, but yet keep the latency for read-write requests at a millisecond level of performance. Particularly as you scale up the number of nodes. Slow is totally fine for cold storage, right? But for apps or databases that are customer-facing, slow really isn't an option. People will bail and just go to your competitors. Now, you might notice I didn't give an exact number because it sort of depends on the exact amount of resource allocated to a single node. But in general, we're talking about thousands of operations per second per core. Now, I said it was a distributed database. So sure, you could technically run it on a single node. But that would sort of defeat the purpose of what it's meant to do. It's a leaderless peer-to-peer system, meaning, any node can do what any other node can do. I'll explain what that means in detail. Don't worry. But this is what helps it kind of deploy across regions and data centers, and the automated self-healing helps ensure it stays available under pressure. It runs anywhere the JVM does, so it's platform agnostic. And since it's not like a single single vendor open source project and owned by Apache Software Foundation, it's vendor independent. Okay, cool. Partitions over distributed architecture is what makes it capable of handling data, right? And I'm talking, tera, petabyte scale. You just need more data, just add more nodes, and then data on partitions just gets redistributed automatically for you. Okay, so a single Cassandra node, like I mentioned, can handle 2 to 4 terabytes, thousands of operations per second per core. Basically, sure, other NoSQL databases are also distributed, but often reads or writes can only happen on certain node types. I don't know if anyone's familiar with things like Elasticsearch. You have master nodes, you have coordinator nodes, you have all different types of node roles, and that can be great. It can also potentially create a bottleneck. Similarly, this sort of leader-follower architecture, the leader or the master node can be a single point of failure, or even if there's multi-master or leader election type things going on, that can impact cluster performance as new leaders are elected. So when I said that every node can do what every other node can do, that's any node can deal with any request, right? Read or write. So everyone has superpowers. Now, with volume and velocity, there really aren't any limits with Cassandra, and you'll notice that sneaky little asterisks down there on the bottom of the slide. You know, we're not trying to be Dilbert Weasley here on you. We're just saying that, you know, you can get linear scalability out of Cassandra, no BS. It just requires you to get the right data model. Okay. Now, the Cassandra community has lots of resources to help you here. But I think simply put, data modeling revolves around creating a schema and modeling your data that will distribute evenly across the cluster now and in the future. So you get that right, and you can get that kind of graph that you see there from. We borrowed that from the Netflix tech blog. They did a benchmark where you know, to prove that adding more servers doesn't have a diminishing point of return, right? Cassandra doesn't do that if you do the data model right. They scaled up in this chart from 45 to 300 nodes, and you see this nice smooth line up and to the right. You know, it doesn't curve off at all, right? So if you want some details on that, Cedric, maybe you could drop the chat in the chat, the YouTube chat, the link to the Netflix blog. That'd be cool. This is now some time ago that this was done, but you know, Cassandra has not changed in that regard since this blog was published. Okay, so I don't know about you, but maybe you're a casual gamer. You like to play games on your tablet or your phone once in a while. You know, you ever run into that moment where it says it's offline for maintenance? You know, gosh, right? So, you know, why is that, right? You know, Cassandra helps address those sorts of issues. You know, in part, it's based on this Dynamo paper, which, you know, is now several years old. It's not DynamoDB, it's the Dynamo paper, the academic concepts that set a baseline for the highly available system, right? That you know, how it was going to deliver that nearly, what, 15 years ago, right? So to Cassandra, high availability doesn't just mean fault tolerant. It also means disaster tolerant. You know, using multiple regions and data centers, availability zones over different regions, multiple servers per region or per availability zone, et cetera, et cetera. Cassandra's replication makes downtime nearly impossible. We've run into clients that have come in that are doing self-managed that are, you know, I can't name the client, but one of them came into a company all hands meeting and said that they hadn't had a crash in years. I'm just gonna let that sink in. Years. Like I don't know a Linux server that can stay up for years. With no leader-follower architecture and multiple live replicas in place at any time, there's no single point of failure, right? Cassandra automatically understands networks so that all of your replicated data inside a cluster's nodes, you know, they're not put in a vulnerable situation like they're stacked up on the same availability zone or the same server rack, right? Now, the driver clients are smart and they're aware of this, so they make it transparent for the app developer with things like smart retries and reconnection mechanisms. And you know, they can auto reconnect to another server or data center, because remember, any node can do any operation. Makes it really easy for the developer in that regard. Now, operations for a huge cluster can be tiring, right? You know, one of our excellent DevRels, Aaron Plutz, you know, used to work at Target, and he can tell you, you know, what they went through, you know, come holiday shopping time. He's got stories.
So, you know, go for it.
Yeah, totally, Aaron. Jump in on chat if you want. But yeah, he lived that. But you know, the clusters are, you know, do have some basic smarts. They are able to scale. They can change data placement. They can recover auto magically, right? There's more to operating clusters than this, of course. But it's good to know what's already handled by the system, right? So you know what to focus on. Okay, you know, I got to understand how to do backups. Okay, I got to understand how to do consistency checks and Reaper and compaction and things like that. All right. Now, Cassandra's trademark, it's hallmark. What is one of the things it's known best for? Multi-data center deployments. You want to go global, you want to go regional, you want to go national, we got your back. Cassandra's got your back. It grants you an exceptional capability for disaster tolerance, and you can bring your data close to your users, right, to keep things low latent for your applications. You know, historically, companies really only had two options here. You know, you could go active passive, or you could go active active. You know, Cassandra is an active everywhere setup. You know, they're not on standby or otherwise passive, right? So, you know, Cassandra's sort of mature and proven replication. It's a big part of how it's able to deliver the linear scalability, the high concurrency, and the extreme high availability that it's known for. Okay. It's also not bound to any platform or service provider. It runs anywhere the JVM does, right? So, you can run in a VM on Azure, AWS, Google Cloud. You can run a bare metal. You can run in VMware. You can run an OpenStack. You name it. It's JVM does it, right? That's the great thing about the JVM. And so, you can learn this once and deploy it anywhere, right? Your database skills will travel with you no matter what job you go to, or what corporate architecture decision or vendor has been selected. You don't have to worry about having to learn Cassandra again, or learn another database management system. You'll never need to re-architect the system as it grows, because you can depend on linear scalability. Okay. Also, it doesn't belong to to anybody, right? Any of the commercial vendors. It's controlled by a not-for-profit open source foundation called the Apache Software Foundation, which you're probably already familiar with if you've ever used things like Hadoop or Spark or Apache Kafka, Apache Pulsar, Zookeeper, Maven, et cetera, et cetera. Some fantastic, excellent industry-leading projects at Apache, sort of the gold standard in many ways for open source. This protects your skills and investments, as well as allays corporate concerns in the long term. Because with open source, it's always possible to read the source code yourself, right? You really need to understand something and go all the way down the rabbit hole, right? You don't have to deal with decompiling, or reverse engineering obfuscated classes or something ridiculous like that. The source code is available for you to learn from, as well as help you troubleshoot, in the event that you really needed to do so in anger. Of course, there's lots of experts, lots of community, lots of support options available. So, hopefully you never get to that kind of a situation. All right, so slides. Yes, hot off the slide press. Let's go. Let's do a little bit here. Cedric, I'm going to turn the share back to you. Go for it.
Yeah, sure. Thank you very much. And we are totally on time, so that's all good. So yeah, it's now time for you to get your hands dirty, for everyone to get their hands dirty. So let's go with some first hands-on. So obviously you will need Cassandra. But as you see before, Cassandra makes sense to be installed on multiple nodes, multiple machines, and it can take a while to install it yourself. So why not using a service that's providing Cassandra for you just with a single click? So today we will use something called ASTRA, ASTRA-DB, astra.datastax.com. So get Cassandra as a managed service, free to use, no credit card. If you use more than 40 million requests per month, maybe we will start asking you for something. But for now, free to use, all your student side project could run on it. No operation, global scale. And inside the same platform, there is also a streaming solution called Apache Pulsar that we won't use today. But hey, so this is why we pick ASTRA-DB today. Nothing to install, very easy to use. So how to use it? Lab 1, setup databases. Okay, so either Aaron or Rags will share the GitHub link with everything on the YouTube chat. You can also use Nightbot, !GitHub, to get access to the README that I do have here on the left part of my screen. Introduction to Cassandra, and here you see first the homework. That will be the assignment for you to do at home this week when the workshop is complete, to get the badge, table of content, and here create your ASTRA-DB instance. And on the right part of my screen, here I do have the ASTRA platform. So the URL for today is here. So we have a short URL for everyone. So again, !Astra to get the URL for ASTRA, and here we go. So as you can see, to authenticate to ASTRA, you can leverage on existing account, Google or GitHub. I will pick Google this time. And let's do it. Timeout. Here we go. And here I see Rack sharing the link for ASTRA and GitHub. Thank you. All right. So when you sign in, I already have a couple of databases here. So you won't have any, But so the first things we will ask you to do, so looking at the screen over here on the left part, is to create a new database. Here the getting started button that will show up, and you will create a new database called workshops and a key space called Cassandra. So each time you need to provide an input in the end zone, you can copy paste from the instruction. Pretty cool, right? But again, ask the question in the chat. We will be happy to copy paste the value there as well if you want to. Okay. We are not in a hurry. I will, let you the time to sign in and create that database. Okay, so create database. We got a question at the same time. So is serverless a database, right? So serverless could be applied to multiple type of system. Serverless, in my opinion, technically speaking, means it can scale to 0. If you are not using it, it's not running, you are not paying for it. It's really driven by the cost, pay as you use. So in the development, you might have heard about functions as a service, Lambda function, Google function, Azure function, Knative. It's really where you're not using it, there is no server running for it. So database, same. If you are not executing your database and it's not really running, you won't get charged for it. And if you need a lot of the database, it will scale as you grow. Okay, so database name, workshops. Key space name, Cassandra. Here, copy pasting Cassandra. And he provide a region. So to get a free region, a free tier, go to the Google Cloud and pick one region that is free. Okay, the region not free, get a small locker over here. Pick one that is free. Okay, and they are part of the Google Cloud. To unlock the others region, if you want to do that, then this is where I will ask you for the credit card. But the free tier have everything you need, and you don't have to provide anything. Okay, so my workshop database is now pending. I already had a database called workshop, so as you can see, the database name is not unique. What is unique is the database identifier. But never mind. So as Peter explained, this is a 3-node cluster, 3 machine. It will take a few minutes to start up, okay? But even then, when you do have your database pending, please give me a thumb up in the YouTube chat. Yeah, just to tell me that, hey, you are okay, I'm not, and then we can move on. Oh, the key space name is Cassandra.
Did you say chat, Sandra?
Cassandra. I don't know.
Okay.
If you want me to spell it in French, that would
yeah.
Cassandra, okay.
Chat, Sandra. Good one. Nice.
Okay. Okay, so I can take this question during the database initialization, and we will go back to slide, and Peter will keep moving, explaining what do you store in Cassandra. So yeah, with Cassandra, store together what you want to retrieve together. So based on what you want to insert, on which node to insert the data. So the insertion, the writes are totally distributed among the nodes. And remember, there is no leader nodes, no master node. So the load is totally distributed. Then when the request comes to a node, it will be added to a commit log, appended to an existing open file, so super fast, and then pushed into the memory. And then you are the client is acknowledged. Acknowledge. You switch me back in French now. Okay.
Désolé, je suis désolé.
All right. Okay. So the client is acknowledged. So it's very fast. You come with the right request. You know on which node to go immediately. Put the data in a already open file. Put the data in memory and acknowledge. And later, either when the memory reach a threshold or you reach a vacation time, everything in memory will be flushed on disk. And if things go wrong and the nodes go wrong before the data is flushed on disk, when you restart the node, it will read what is in the commit log and will be able to catch up and will not lose any data. This is why it is so fast. Yes, so keep seeing some sum up. I think we can move on. So now, either you listen to Peter going to what do you store in Cassandra, or you totally hands-on person and keep going at your pace with the 2, 3 before I'm going there, as you wish. And now, Peter, I think you can.
Cool. Sounds good. All right, 1 second. I'd go for the hands-on option over listening to me personally, but hey, you know what? You know, we'll do what we can here. All right, let's see. Is that showing up, folks? Are we seeing the holy scripture of Cassandra, page 1, paragraph 1? Excellent. Okay, so in the beginning, because the lords and ladies of Cassandra said that all servers are created equal. So basically, you know, let's just talk a little bit more about this active everywhere idea, right? Why is peer-to-peer architecture important in distributed databases in particular? Okay, so you know, we look at the traditional kind of leader-follower architecture, right? You know, you select one server amongst the cluster as a leader. That leader is responsible for making decisions on behalf of the whole cluster, propagating those decisions to all the other servers. Every server at startup looks for an existing leader. No leader found, it triggers an election. The servers will only accept requests after a leader is successfully elected. I'm going to refrain from making Trump jokes while we're reading the rest of this, but only a leader handles the client requests. You know, if the request is sent to the follower server, the follower has to forward it to the leader, right? They can't deal with it. So the leader election within a cluster, you know, it works well, especially with smaller clusters. But when you get to big clusters, maybe even a couple hundred, 1,000 nodes, you know, typically a lot of distributed systems will use an external store like maybe Zookeeper or etcd because those internally use consensus, have their own robust consensus algorithms and provide some linearizability guarantees. You know, those are great options, but, you know, not all databases, distributed databases out there, you know, are using things like Zookeeper or etcd. You know, they often roll their own, you know, and there's a lot of different options for distributed consensus. You know, Raft, Paxos, et cetera, you know, and Accord is being kind of a new one on the scene that we'll hopefully learn more about in the future soon. So the peer-to-peer architecture kind of addresses this issue. With this setup, data is replicated across multiple nodes, all of which are equal. No single node can bring down an entire cluster. A typical peer-to-peer topology, you know, you've got 3 or more replicas for each data set. So a NoSQL database like Cassandra that implements a peer-to-peer architecture provides yet another layer of resilience, right, for this sort of high volume, low latency apps. So you as a developer, you know, you do need to do things like denormalizing data, and you're maybe a little bit more aware of the logical and physical data models as opposed to maybe something like a document database. But you know, the payback really comes to you with the scalability and the availability. Okay, let's talk a little bit more about what I mean when I say data is replicated, because obviously distributed consensus is one of the hardest things in computing, next to off by 1 errors and naming. You know, replication factor. This indicates the number of nodes used to store each partition. haven't defined a partition yet, don't worry, we'll get there. So that means each node is responsible for up to X partition ranges, where RF equals that X value, and stored on multiple partitions at the same time. So data arrives at a node that acts in the role of coordinator, because again, any node can be a coordinator. So where does the coordinator send the data this time, right? It's replicated to X number of nodes depending on the replication factor. The default in Cassandra is 3. 3 proves a pattern mathematically. 3 is the magic number. It's a good number to use for a lot of reasons. But that's, in a very small nutshell, how the replication works in terms of where data is placed. So what does this look like in code? CQL is a query, a data description language for Cassandra that is a subset of ANSI SQL, and is meant on purpose to be very familiar to you if you're an SQL developer, syntactically. So we use it for both setting up the database, configuring it, and then of course querying it and interacting with it. So here's how you create a key space in CQL. Wait a second, hold on. What's a key space? You might rightly ask. Key space, kind of like a relational schema, a schema in relational databases. So loose analogy. We'll define that more crisply as we get on. So the key space name, you're just saying here in the syntax is population, right? And then when you specify the replication, you can specify a strategy for how you want to distribute the replicas. There's some complexity here. There's some additional configuration options. There's lots of handles for you to handle your situation, but network topology strategy is a good strategy that places replicas in a network-aware manner. So that's a great starting point. Here, we're going to say we want 3 replicas in our data center. If we had more data centers defined, we could specify separate RF or replication factors for each data center by listing them here. So you can really control it at a per data center layer. But that's what it looks like in code, in CQL. So Cassandra wouldn't be a very robust database, however, if it only stored 1 copy of a partition in one place. If that was the case, wouldn't take a lot before a single failure could mean missing data or worse, a failed database operation. So cue your replication factor. You'll notice there's 1 ring here, right? And we're denoting an RF of 1, which basically means 1 copy of that partition on 1 node. And don't worry, again, we will define what partitions are in detail. Okay, so let's say your rows with your USA data for New York and Los Angeles, it's a 1 copy on that 1 node. Now, if you increase to an RF of 2, now I have 2 rings, and I have 2 nodes that contain the USA partition data. Great. Similarly, you guessed it. If I define it, tune it up to 3, which is the default. Now you add another ring, and you got 3 copies on 3 different nodes. So, like I said, that's the standard in Cassandra, and it gives a solid balance between availability, performance, and consistency. Okay. So let's dive into a little bit of database internals so it's clear to you how things work when we say that data is distributed. What does that mean? Well, one of the questions we get asked a lot here on these, yes, only once is complicated. Yes, exactly, Cedric. One of the questions, yeah, it's complicated, TM, exactly. One of the questions we do get asked a lot is, if it's a distributed database, I have some set of data, how does it know? How does Cassandra know where to put the data or how to get it later when I want to read it? So it's divided up into what we call partitions. Take a look at this example table here in the slide. We have 3 columns, country, city, and population. Country, that's our partition key, right? We'll show you what this looks like in CQL as well, so don't worry, it's not complicated to define. Now, in this case, what we're saying is that we're dividing up all the rows here based on the country value. Now, there are multiple rows with the country USA, France, Canada, Germany. Since they have the same partition key, like Cedric was saying earlier, data gets stored together within a node, and data gets automatically distributed around the nodes in the cluster according to that partition key. Now, let's look at this example. The same data, we've just broken it out, taken the data from that table and distributed it around the cluster visually here, like it actually happens in Cassandra under the covers. So notice how rows with the same country value, they're grouped together, right? They're literally stored within the same physical partition on disk. So later on, if I wanted to know the population for every city in the United States, I could read a single partition and you get all your results with an extremely low I/O cost, right? that's part of the awesomeness of Cassandra, is that you're sort of storing the data like you want to retrieve it when it comes time for your application. You're thinking about these queries ahead of time and storing the data exactly like you're going to retrieve it, so it's wicked fast. Okay, then you choose your partition your key for your table. Cassandra just handles all the rest. It does all the data distribution for you. Okay, let me pause there for a second, see if there's any questions related to the slides. Doesn't look like it. Cedric, if I missed something, let me know. But I'm going to continue on.
I think you're good.
Okay, cool. All right, just checking.
If I'm not screaming,
okay, yeah,
you're good.
All right. Yeah, so it's like any other workday then. And if you have questions, folks, yeah, please don't hesitate to drop into the chat if you want to ask about something on the slide or get into more detail. Okay, so what does this look like in CQL, Cassandra Query Language? Again, should look pretty familiar to you if you've come from the relational world. So we start with a key space. You see there's the create table command. Population is your key space. And then the table name is population by country city, right? Then we're defining a couple fields and their data types. Country is a text, cities a text, population integer. And then here's the interesting part. This is this is where it gets interesting. Your primary key, partition key, and clustering columns. So for all tables in Cassandra, you have to include at least one partition key, right? In this case, we're defining it as country. So we're partitioning by country, just like we did visually in the past couple slides. And so, anything else that comes after that is a clustering column. Now, notice how you've got this like inner parenthesis around, country and city here, denoting that it's kind of potentially a composite partition key. The reason why we're using the parenthesis is in case you do define a composite partition key where you have more than one value as your partition key, or you have more than a bunch of clustering columns. The parenthesis just kind of tells CQL which are the ones that belong to your partition key. So it's just a good code, readability and cleanliness habit to include this parenthesis, even if you only have a single volume. All right, then it's very clear which one is your partition key. And if you decide to go composite, again, what's partition key and what's clustering columns. Okay, cool. So that's what it looks like in CQL. Pretty straightforward. Not terribly different so far from standard SQL, even though the primary key concept, partition key and clustering columns, is indeed a bit different. Okay. Now every table has dedicated or more than one partition key, country in this case, right? Now, each node has a range of partitions assigned to it. The numbers here are just arbitrary to keep the example simple, but you get the concept. These are called partition tokens. Every node is assigned a set of tokens that they own. So if we look at the orange bubbles here on the lower part of the slide, if we start at the left node, that owns range 1 through 25, and the next one, 26 through 50, 51 through 75, and so on. So when you add, and so on around the ring, right? And when you add a partition key to a table, that value is automatically hashed out using a murmur3 hash into an integer token value. So, USA New York becomes 59 New York, right? And that's how Cassandra knows where to store and retrieve your data. You can think of it as the address of your data almost, the partition key. So from left to right here, Toronto, Montreal, numbers 12 here would go in that first node that owns range 1 through 25, right? And then who in chat can tell me where Los Angeles and New York would go? Which node would it be if we're counting from the left with these orange circles? So which node, starting from the left of these 4 orange ones, would own the New York and Los Angeles data? Exactly. So, Salmin, you got it. Yep. Yeah. Hemant, Anjali, you got it. Exactly right. Exactly right. Yeah, pretty straightforward, right? I mean, this is why Cassandra, it doesn't take it a lot of computational overhead to figure out where stuff is, right? Because it's a pretty simple address. Okay. Awesome. So why partitioning? Well, as I was literally just saying, because scaling doesn't have to be hard or shard. I see what you did there, Cedric. That's funny. One of my friends had a T-shirt from a conference that says "I sharded."
Yeah, it looks analyst jokes.
Distributed database jokes. Okay, folks, we've got jokes. So, you know, these volumes of data are just not going to fit into a single server. So you have to spread them out over dozens or hundreds of thousands of servers. And, you know, there are some, you know, some of these ways of spreading them out are you know, there's always trade-offs, right? Nothing is categorically better than something else. But, you know, for Cassandra, you know, this works. Our technology works pretty well. Now, token ranges get recalculated if more nodes get added to rebalance data. So in plain English, if you add nodes, you've got more to spread the load across, right? So each node can own less and less and less tokens in the range, since there's more nodes to share the load. If you scale down or scale in, depending on what you'd like to say, more partition token ranges will then get repacked into fewer nodes, right? So if you have a 4-node data center, what happens if you add a node? Well, okay, instead of having to own 25, a range of 1 to 25, you can only own what, you know, the first node only now has to have 1 to 20, right? Similarly, if you shrink it down, oops, I've got to own more token ranges because I've got less nodes to do it, spread it across. But, you know, there's no downtime here. All of these scaling operations are live at runtime, zero downtime. You know, this is just the auto magic of Cassandra at work, and not something you need to handle or deal with, but, you know, good to be aware of and understand the database internals. Yeah. Okay, cool. Thanks, Aaron, for answering that question from Narayana.
Yeah.
Appreciate it. Okay, so then, you know, now let's add something else here. Let's talk about replication factor. We're going to talk about that a little bit more in a minute. But if the default is 3, these partition token ranges are duplicated, and then they're sort of offset across the available nodes in the cluster for fault tolerance and load balancing. So, you know, just as you see here in the picture, if you have an RF of 1, okay, you have 1 set of data across 4 nodes. If you have an RF2, you have 2 sets of the data, just distributed differently, right? Because it'd be sort of silly to put them on the same node, because, right, you know, then it wouldn't be fault tolerant, and nor would it load balance as effectively. So, you know, you can see here it's the same data, it's just kind of offset and spread differently across the nodes. Cool. So a little bit more about replication factor and how data is stored and retrieved in Cassandra. Let's start with the default, which is the RF, or replication factor, of 3. So if we want to write some data, you know, maybe this USA partition from earlier, you know, the request comes in, a node is you know, chosen to handle that request. We call that a coordinator node. It's any node can be a coordinator, right? Because remember, any node in Cassandra can accomplish any operation, right? You know, it's just the node. It's just the name given to the node that's acting in that role at the moment. You know, at the moment that request comes in. Okay, so, you know, this data, you know, let's say 50, you know, the integer 59 comes in, or maybe that's a partition token and a set of rows. But anyway, all the nodes in the ring can handle that operation. So great. You know, let's hand it to 67, 83, and 0, because needs to be replicated 3 times, right? Because we've set the RF of 3. So that means there's 3 copies of this particular partition identified by 59 here in the cluster. Okay, cool. Pretty simple concept. We don't need to you know, belabor it. And then that 59, again, that's just the partition token, right? That was hashed out of the partition key for the data we're writing. Yeah, so the coordinator just basically forwards that database write operation to all 3 nodes. Each node stores a copy. Pretty simple. Okay, now each node and the Cassandra drivers themselves as well know the token allocation in the cluster. So it means it's token aware. So your app can, you know, via the driver, clients can contact almost, you know, literally any server and still get the right answer, right? Again, part of this power of all nodes, you know, being able to do all operations. So let's talk a little bit more about globally distributed. What does that mean? We kind of hinted at this earlier, that the Cassandra is well known for this. So with this concept of data centers, together with replication and all the other things we've talked about, it makes it pretty easy to deploy Cassandra in any region or multi-region. The last one I think is particularly powerful, because you know, most databases you can deploy a single region anywhere globally, right? That's just the cloud these days. But a single database that spans multiple regions, or a multi-region database, that means you need to to have replication that works and is fast and is available and all those other adjectives, right? You know, and since Cassandra runs anywhere that the JVM does, you can run it on any infrastructure provider, public, private, you know, hybrid cloud, multi-cloud, you know, all of those things, you know, bare metal, you know, all of those work. So you can bring the data to your users and to your applications in the region that they're at, meaning that latency will be low for your users that when they're interacting with asking for data from the database. And that's very, very, very important. Yet you're not sacrificing consistency, availability, or scalability. Okay, so folks, in the YouTube chat, what is the biggest, and we have not given away this answer previously, so this is a real question, warning. This is an actual question that will cause you to think. What is the biggest issue with replication? Go ahead and respond in the YouTube chat. What's the biggest problem with replication in general, not with like just Cassandra, you know, with any, right? Okay, yes, TP got it first. Although Vino, you hit it, but just sideways. You hit it from the Cassandra particular perspective. I was kind of getting at what's the general issue with it, and you nailed it, and everyone's got it. Yeah, exactly right. Yep, data consistency. That is the issue. How do you deal with the fact that things are spread across a network? Right. This is the existential question of distributed computing. So, you know. So many things in Cassandra are aligned around multiple layers of defense. So many things in Cassandra are aligned around mitigating that risk, right? So let's look at a scenario here. This is a default replication factor 3 scenario, right? So that's why you see 3 arrows going there from the new value of $13, right? New value is written, you know, let's say a writer 1 writes this, you know, new variable, you know, X is equal to $13, right? Since the RF is 3, the write request is sent to all 3 servers. Now, let's say it's successful on server 1 and 2, but it fails for server 3 there in orange. Now, if later your client, your app, you know, via the driver, your client reads the value of X from server 1 and server 2, well, it gets the latest value of X is 13 because server 1 and server 2 have that latest value. Now, let's say that another client from a separate application triggers a read for X. But server 1 and server 2, you know, some disaster happens. They're aliens fly in from, you know, out of town. There's an earthquake, tornadoes, something happens, and server 1 and server 2 are down temporarily. So that means, you know, client 1 needs to read it from server 3. Now that has the old value for X of $12. So C2, client 2, gets that old value, even when, you know, the first client got the latest one. So you have 2 consecutive reads here from 2 different apps that, you know, basically say, wait a second, the latest value is it's not getting the same answer, right? Now, sure, once server 3 came back up, you know, the earthquake was healed, the tornado abated, subsequent reads would give you the latest value, sure, right? Now that assumes, you know, of course, some sort of read repair or anti-entropy repair process is running in the background, which of course it is with Cassandra, but we'll get to that later. You know, the rest of the servers will get that latest value as well, eventually, right? This is the eventually consistent way. Cue Mandalorian GIF, someone, but there is no guarantee provided by the storage cluster, right? That to make it once a particular value is visible to those clients, all subsequent reads are going to continue to get that value even if it fails. So how do we deal with this potential inconsistency? Now, distributed consensus, I'm going to preface this by saying distributed consensus algorithms are some of the most difficult things in all of distributed computing. So it requires a multi-layered sort of defense, you know, much like security does, right? You know, you have a security posture, you have multiple layers of security. Why? Because security is hard, and people are trying to break it. People might not be actively trying to break distributed computing, but it is indeed very difficult. So what do we mean by that layered self-defense, right? Okay, let's look at one strategy to avoid potentially inconsistent state. Like we can call this hints. Now, let's imagine we want to write some data. Let's look at that USA partition from earlier. As the request comes in, right? Any node's chosen to handle it. acts in the coordinator node role. And then it is replicated, since it's an RF of 3, it's replicated to nodes 67, 83, and 0 there. Okay, great. With me so far? Excellent. All right, now then, one of those nodes catches on fire and it's down, right? So we've only got 2 of the 3 sources available. Now, we have this ability called a hinted handoff. It's a persistent data consistency mechanism that's built directly into Cassandra. So when a node goes down, the remaining nodes will save any mutations, in this case a write, for those nodes locally as a hint. And then the hinted handoff makes sure that that write operation gets to all the nodes that hold those replicas. Now, hints are stored for about 3 hours by default. So if the node isn't able to come back within 3 hours, either you need to trigger a repair process, or, worst case, you could destroy the node and bring it back into the cluster as a new one, which would sort of refresh and rebalance all of its data from a known good cluster state. Okay. Right. Sorry. I failed you on the animation there. But yeah, this is one of the many sort of robustness features, right, that's built into the core of Cassandra. There's all kinds of other things. If you catch up with Aaron Plutz, he'll tell you all about his adventures with NodeTool. There's Reaper. You can set transaction consistency levels on a per transaction basis, which is pretty mind blowing when you think about it, and a lot more. Okay. Now let's talk about Cedric's favorite section, cap theorem. What does that mean? Well, Eric Brewer from Google defined this a number of years back, and it has since ruled many people's worlds in the cloud and in distributed computing. So it talks about the trade-off between availability, consistency, and partition tolerance. Okay, what does that mean in plain English? Well, availability is, hey, you ask for data, you get an answer. Is the service up? Not making any claims here about whether it's the right answer. Just does an answer come by? Does an answer come back to me? Consistency meaning, do you get the same answer from all the servers in the cluster that would be in a position to answer that question? And then partition tolerance is your ability for a distributed system to survive a network failure. Suddenly, one side of the network or one node can't get through the network to another part of the cluster. Okay. Put another way, right? Uptime. Availability is uptime. If a failure of one or even multiple servers, leads to no response, or leads to a response, your system is considered available. Right? Consistency is, what I was saying before. No stale data. You ask for something, you get the most recent value. Right? If you get a different answer or older information is returned, your system is not in a consistent state. And then partition tolerance, like I said, the ability for nodes in the network to suddenly, or the communication link is severed. Suddenly, part of the network is unavailable, and a half of the cluster can't talk to the other half of the cluster, or something horrible like that. That is one of the more difficult things to deal with, and most of a huge part of the focus of what Cassandra does not compromise on is really tries to avoid the issues caused by partition tolerance and network unavailability at all costs. So it's important to remember that this is talking about a cap theorem. This whole conversation is really about what happens in a failure mode. When everything's working fine, you can be consistent, available, and partition tolerant, and all at the same time. Great, things are working great. It's when there's a failure condition that you have to potentially choose 2 out of these 3 things. Unfortunately, you can't be in that little sweet spot right there in the center in black, right? You have to make you have to make a choice there. Every distributed system, not just Cassandra, right? Distributed applications, distributed databases, anything that's distributed has to make this choice. So you have to choose 2 out of the 3. And like I said, Cassandra really strives to avoid inconsistency above all else, right? So in a failure scenario, Cassandra's design philosophy was that you can configure and choose your compromise. You can choose your own adventure here to either be consistent and partition tolerant or available and partition tolerant, right? Different systems, different databases, they make different compromises and they have different design points, but that's the way that Cassandra works. So that's why there's some confusion out there sometimes as to, often people when encountering a new database will ask, hey, is it, you know, where is it on the CAP theorem? You know, is it AP or is it CP or something else? You know, and there is a little confusion out there in the market. You know, is Cassandra an AP or CP database? Well, yes, is the answer. It's both. It's configurably consistent, right? But it cannot be both at the same time, right? It has to be one or the other at any given query. Now, since, as I said, Cassandra, you know, prefers availability slightly over consistency because it's an eventually consistent database, but you get the flexibility to tune the consistency depending on your use case and at the per transaction or per query level. Okay. Now, the consistency level is one of those tools that we you know, the system uses, one of those layers of defense along with hints that it uses to you know, ensure consistency. And you can set the consistency level, you know, that you want to have. And that basically defines how many confirmations that the client, the driver client, your application, is going to wait for before, you know, the response is dispatched back to your client and, you know, a definitive answer is delivered. Okay. Now, like I said, it's configurably consistent, right, on a per query, per transaction level, which is awesome. So you can set it here, and there's a number of different consistency level settings. There's some more advanced ones like local one or local quorum or each quorum that I won't cover here. I'm just going to cover some of the basics, just to give you the because this is an introduction to Cassandra. There's lots more enablement material here on our YouTube channel that would get you into the details here. Now, we often recommend that write operations. Oh, excuse me, sorry, I'm jumping ahead. Right. So mixed consistency levels are good, right? It doesn't have to be one way for the entire, you know, life cycle of your application for everything that every query that your application could potentially execute, right? You can also mix it, you know, even within a single, you know, a single aspect of the application. So one best practice is that, you know, you could do write operations at a quorum, but for reads, you could maybe be more flexible and you could try maybe read it at a consistency level of 1 or 2. Now, what does this mean really? Let's kind of examine and get into it. What is the impact here during the write and the read of data? What does this mean? Okay, so let's look at the simple case, consistency level 1. Now, in this scenario, your replication factor is 3, so you're copying data to 3 nodes, right? You're copying a single partition to 3 nodes. And let's, you know, client comes along, writes some data to a node. The request is routed to those the correct replicas if it needs to be, asynchronously, and then, you know, concurrently. So 3 separate network calls to these 3 replicas. Now, the first answer that comes back from either of those 3 nodes that indicates success, great, we're good, right? The response is returned to the client as definitive. You know, you got your data back. Okay, now let's look at another way to get strong consistency using quorum, which is often what we recommend. A write operation with quorum now only requires a response from the majority of the nodes available. Now, in this case, we set RF as 3, so what's a majority? 2, right? 2 out of 3 is a majority. And then we can also read consistency level quorum. You know, we can also read using that quorum consistency level, and we're guaranteed to get the most recent data. As long as we can kind of guarantee the overlap between reads and writes, we know we're going to have a strong consistency here. Great. Now, all is another interesting one. A write operation with a consistency level setting of all requires responses from all 3 of the replica nodes because, again, RF was set to 3. You can also read, not just write operations, but you can read using a consistency level of all, and then you're guaranteed to get the most recent data. Yeah. All right. Now, it might be tempting to think that the consistency level all is just, hey, this is, you know, we should live here, right? Why not? Why do anything other than that? Well, that's great, but, you know, when everything's in sync and everything's working correctly, but, you know, remember CAP theorem, right? It's as General Admiral Akbar famously once said, it is indeed a trap, right? CAP theorem is always there in a failure condition. So if you choose consistency, it is at the expense of availability. So, you know, that means, you know, if one node goes down, the request fails, right? So that's not, you know, that may not be good. Okay. Now, one trick that has kind of emerged, you know, over time is that, how to use these two things together, right? If you need immediate and strong consistency, what we typically recommend to our customers and our users is that the simple formula here, the consistency level of write plus the consistency level of read should be greater than the replication factor. Okay, wait a minute. So what does that mean? So if reads and writes are set that way, you're gonna be immediately consistent even if you lose one server. So RF is 3 in this example, right? So consistency level is quorum for write and read. In this case, I guess it's set to quorum. So if RF is 3, that's 2 for each, right? So consistency level of write is 2. Consistency level is read is 2, which is equal to 4. Needs to be greater than replication factor, which is set to 3, which is currently not set that way, right? So if you wanted, let's say, just to play this out, immediate consistency with 5 nodes, an RF of 5, and a quorum setting for read and write, you would need to set your RF to what to get immediate consistency? If anyone wants to guess and try to beat me to it, if you wanted immediate consistency with 5 nodes and a quorum setting, what would you need to set replication factor to get immediate consistency? That would be, okay, I guess maybe we do a Menti for this at some point, but that would be RF is 4, right? Because, or actually, wait, did I get that right, Cedric? No, wait a minute. It would need to be higher than that, wouldn't it? Immediate consistency with 5 nodes would mean 3 plus 3. It would need to be 7?
Okay, so it's based on the replication factor, not the number of nodes. So let's say the replication factor is 3. You read with quorum. Quorum is the majority of the node. So 2 over 3. So you get 2 responses.
Yep.
And among those 2 responses, you are sure that one of them is the latest, and you get rid of it.
Yep.
The other side, same. When you write with quorum. Quorum, majority of the node, so 2 over 3. Okay.
Yep.
So consistency level to write 2, consistency level to read 2. 2 plus 2 is more than the replication factor 3. Good to go. With that, anytime you read something, you are sure to get the latest version. Now, let's say, and you talked about that, the replication factor is 5 for some reason. Well, you read with quorum. So quorum for 5 is 3. You get the majority of the node. And you write with quorum as well. 3 over 5. 3 plus 3 is 6. 5, you're good to go. That's more related to the replication factor rather than the number of nodes.
Right. Okay. So I was looking at the greater or less than sign and I read it backwards. So, okay, got it. All right. Pretty simple. Cool. Thanks for that. And then let's talk a little bit more about tables and partitions. So hopefully that's clear. Thanks for that, Cedric. And then, yeah, let's talk a little bit about tables and partitions very briefly. We're not going to get into this too deep because this should be pretty familiar to everyone that's worked with a relational database or, geez, even a spreadsheet or a Google sheet for God's sake. So, a cell, right, as we all know, intersection of a row and a column, right? You know what this is. This is what's holding your data. And then a row being a single structured data item in a table. So, we've got, 4 cells here, 1, John, Doe, Wizardry, right? They're all related, however, together in a single row. Now, in Cassandra, partitions are the basic physical unit of access. So this is how, as Cedric was saying earlier, data is stored together on disk, right? Mm-hmm. So to the very right, that's this way. Sorry, zoom's a little bit of a mirror here. All the values are wizardry, right? Except for 1. So in this example, we've set department as our partition key, right? We're partitioning by department. So I have 3 rows here, and given that each one of the 3 rows has the same partition wizardry key, they're all stored in the same physical partition, right? So they're stored together. It stores together what it retrieves together. So if I was to say select star from this table where department equals wizardry, I would get back all these values. All right, now if we look at the table that has multiple partitions, again, 3 rows here, that hasn't changed. But let's look at department. So department is wizardry, dark magic, and DevRel, right? And then and so even though you have 3 rows and you have a single logical table, you would say to select star from this table, you would get back those 3 rows with the wizardry, dark magic, DevRel in it. But you'd be accessing 3 separate physical partitions in the cluster. And that's what I think is, it took me a moment to get my head around when I first joined the company, was that, you're sort of aware of this network topology, but in the way that you structure the layout of your data does have a relation to this, it has an implication to what happens underneath the covers with the network, right? And so by being aware of that, you can really get, and designing appropriately for it, you can really get all the promises that Cassandra delivers, with no compromises, as long as you're kind of doing things that are aware of that. So, Cedric, why don't you show? Maybe we can do a hands-on, and we'll get people hands-on keyboard and show people how easy it is to create tables. Why don't you take the screen share?
Yeah, exactly. I'm sure now people want to play more with the database. So, but it's really useful and important to explain how the architecture works under the hood, to explain how the database can recover and can scale easily. Because then you will realize that the tables, the data model is really based on how Cassandra works. Okay, so lab 2 create table could be pretty fast. So let's see. Back to my screen. Oh, I was signed out. Okay, let's sign in again. And let's go to big 2, create tables. So the first things that InBiz ask is navigate to CQL console. Okay, so CQL stands for Cassandra Query Language, as Peter stated before. And so I select my database here in the list, and I'm looking for this tab, SQL console, over here. And it will pop up this shell, CQL SH, the shell for SQL. No need to provide any user password, SSO, it's done. So we told you inside a single case, you can have multiple key spaces. Key spaces, logical grouping of table, same as Oracle schema. And the good pattern when you implement an app would be 1 app per key space, because this is also at the key space level that you will set up the replication factor, the RF. So let's see. Here, if I describe the key space, you see all my key spaces over here. Okay. And some are system for internal use at Cassandra. The one that we will use is Cassandra. Cassandra. Okay. So here, maybe I can show you, just describe key space. Describe key space. Cassandra. As of now, it's empty. So the command that is returned is just the command to create that key space. And here, just to show you that in ASTRA, the replication factor is 3. And as of now, you are working with a single data center, but you can have multiple data centers if you wish, and have data distributed across the world. Okay, so what I'm doing now is use Cassandra. So just to change the space name and not having to provide the prefix Cassandra in any of my requests. The shell know that now I will work inside that key space. Okay, so let's see. Create the, as you can see, very close to SQL. The type are not exactly the same. So here we do have text instead of varchar, UUID for unique identifier. And the primary key is it does have multiple parts. One part of the primary key is called the partition key, to say how do we distribute the data among the partition, among the nodes. So all the token slides that Peter presented before. But here, it's the same. Yeah, that's true. You can have table with where partition key is the same as primary key. That will mean the unicity of a record held by the primary key is totally defined with the single field. So it will be both partition key and primary key. You will have a single record per partition, totally fine. So here I'm doing that. And see, I do also create if not exist. So there is this nice check before. And now if I describe the table or this table, I will see my table users. Okay, great. Maybe another one I could explicitly describe table and provide the name of the table. It will show more info regarding that table. So exactly what we have designed, column name, primary key and everything. And also a couple of metadata that the system has put for me, but that you can customize if you want, like the compression, the compaction strategy, the time to leave. And you could have access to those steps, but not in introduction to Cassandra. But yeah, for you to know that's metadata are set for you. Okay, so now let's describe table. What I can do now is create table for post. So post by user and post by room. It seems weird right now, but it will be explained on the next slide. So here, we will have exactly the same table. Look at that. User ID, post ID, room ID, post ID, user ID, text. So two tables to save the same data with the same fields. So what is the chance beside the name of the tables? That's the way the keys are built. Here, the primary key is user ID, post ID. User ID is the partition key. Data is distributed among my nodes using user ID. So if I want to avoid to do a full scan cluster when I look for this table, I always need to provide the value user ID in the where clause. This is how Cassandra will know where to look. So associated with one table, you have a set of valid queries. And if you need two queries to request against the same data set, it's very likely that you will need multiple data, a multiple table. The data is replicated in multiple tables. The philosophy of Cassandra is storage is cheap. And this is a trade-off to be able to do millions of requests per second, even if you have terabytes of data. This is what the relational database was not able to do, even with the OLAP strategy. Now you save the data in tables that are optimized for one particular request. And now if I describe the table, here you go, you will see my 3 tables over there. And with that, I think we can go back for the last session part, slides part.
Sounds good.
Before going to the last lab. And
cool.
Yeah, over to you, Peter.
Thanks. All right. Yeah, I love your point about the full table scan, the dreaded words that any Cassandra user will ever hear. If you haven't sort of gotten the idea behind it yet, that is something to be avoided, right? That there's a lot of, by defining those queries up front, like Cédric was just showing you, you're storing data like it's supposed to be retrieved. It's all contiguous. It's super optimized for reads, but it's not, for analytics, right? It's not meant to sort of, hey, I'm going to ask you arbitrary questions, because then you get at that full table scan. You want to have them, You want to have them known up front. Okay, so let me share this. Is that showing up, the agenda slide now? Are we rocking and rolling?
It's coming. I think you are sharing now.
Cool, awesome. All right, so let's talk briefly about data modeling. And this just kind of this, good segue from the point that we were just talking about here, right? So that, you're, much like a relational database, you need to have a schema defined up front before you can do anything, right? Before you can't just, it's not like a document database where you can just throw a JSON document at it and not have any pre-work or pre-thought gone into it. You're creating a structure for your data to be organized into so that it can be, written and retrieved efficiently, right? So very similar to relational data modeling. Not quite the same, but similar. We're going to start off with, your data. We're going to analyze your data set. We're going to look at your, you're going to look at your relationships, your properties, your entities in a relational database, and then you generate your data model, and then, you normalize it. So, but then from after, that, from the application standpoint, from the developer standpoint, if you're using a relational database, then what? Right? Well, then you take a look at, I don't know, whatever ER diagram, entity relationship diagram, or whatever you designed, whether that's, through your DBA or your data architect, or whether it's you yourself doing it, right? And then you're using that as your source of truth. That would determine, well, okay, what queries does my app need, right? And then, okay, how do I write those? How do I determine them? How do I design them, right? What tables, would I need to join, that sort of thing. So that's kind of how it would work on a relational data modeling, right? You're thinking about your data first, then you're modeling it, then you're thinking about the application, right? So with Cassandra, it just flip it around, right? So you start everything from the application perspective. So watch what happens, right? It's actually ridiculously intuitive when you start to think about it like this. Like, what query is that click on the user interface going to trigger? Or what query is that API call going to need, right? So we're going to start with the app workflow. We're going to start with the application. We're going to use that to generate our data model and our queries and everything, and then we apply data. So you might be thinking, well, wait a second, does that mean I need to come up with my query ahead of time? Well, yes, actually, it does. That's one of the reasons why it's so efficient. And again, why you don't, typically use Cassandra for analytics or ad hoc query workloads, right? Because you're defining this stuff up front. That's why it's so fast. So we're going to go through this process right now and show you how it works. But once you've done it like 2 or 3 times, it's really quite intuitive. So this is the overall kind of workflow of what we're going to do, right? So we're going to start with the app workflow and then figure out our entities and our relationships. Then we figure out our conceptual data model. And then we figure out our app, our app workflow. If you've done any kind of work with a relational database before in the past, you're going to recognize a conceptual data model. This shouldn't be terribly foreign to you. No pun intended with foreign keys. So the application workflows, that's really what is your user doing as they're working in your app. You could literally draw this in a Figma or a whiteboard or a cocktail napkin. This is what happens in the user interface. Or, if you're developing an API, what API calls are being made. Now, we're going to take the app workflow and the conceptual data model, and then we're going to use that to start mapping those to our logical data model. Then we refine the logical data model a little, and then we optimize it a little bit. And if we need to, we end up with a physical data model. Okay, so that's the high-level process, right? Just kind of describing the overall flow before we dive into specifics steps. And then, as it says right there, very helpfully at the bottom of the slide, one way you can boil out a lot of what I just said into a very quick mnemonic is, a query per table, right? Is a good way to think of things. Okay, so this is our conceptual diagram. Let's say we're doing like a YouTube kind of application or a video, website of some sort, right? So, in this case, we've got users, we've got videos. So when you look at the videos, what are some of the attributes of videos? Well, we got comments. Users can also make comments. So there's a relationship there. So if you look at users and videos, you have a relation between users commenting on videos and videos being commented on by users. So, but it's interesting to notice that both, users and videos have this set of attributes. Users have email, they have an ID, Videos have a title, description, so on and so forth. Now, by using your ERD or entity relationship diagram, you can start to map out what those relationships are going to look like. Right? Okay, so relatively straightforward. Let's move on to the app workflow. So this is kind of your, again, we're sort of thinking like a YouTube or a video watching application, just as an example. In the first use case, you're opening up a user profile. Okay, every app ever invented has some concept of a user profile, right? So nothing too crazy there. User logs in, maybe opens up their profile, and now they want to see all their activity, right? In this case, for a video website, that's comments, right, across all of their videos, right? So like when you logged into LinkedIn or Facebook or whatever, and you kind of just see your activity feed and all your recent activity of all the stuff you've done lately. So you want to find the comments related to the target user using its identifier. Again, probably like a user ID or something. So, and usually you want to show the most recent ones first. So you want to see things sorted, in time order. Now, the second use case, a user opens a video page. So they're going to go to some specific video page, right, to view it. And they probably want to see all the comments that everyone has ever made about that video. So the first workflow, if we boil it out to kind of attempt at pseudocode here, you're doing what? You're finding comments related to target video using its identifier, most recent first. And then, so for the second one, for some video that you click on, you want to see all of its comments from all of the users using the video identifier, some key, and then again, showing all those comments most recent first.
Yeah, and right? Peter, they're just two different screens from the YouTube. So the first screen is your home page. As a user, when you sign in, you want to see all your comments. Yep. And the second is just a video page where you want to see all the comments for video. And of course, you want to see the latest at the top of the screen.
Perfect. Exactly. Yeah. Thanks for giving a better visual for it, no doubt. And then, yeah, it's like if okay, so the next thing you can do is some pseudocode, right? We almost did that. You heard me doing it verbally just a second ago, right? So you're finding all the comments posted for a user with a known ID on that profile page that Cedric just mentioned. And then on the video watch page, you're finding all the comments for a video with a known ID showing the most recent first, right? Okay, so now let's bring it to a logical data model, all right? If we start, we're going to do we're doing a query per table, right? So we have two tables. If we start on the left here with comments by user, so we've got user ID, which has a K annotation after it. That means it's a partition key, right? And then as you remember from before, what are the components of your primary key? It's a partition key and or clustering columns, 0 or more clustering columns. The K, as I said, indicates your partition key, and then the C means a clustering column, and then the arrow indicates the sort order. So what this says, right, is that with user ID, I want to, again, partition by user ID, and then I'm ordering on creation date and comment ID. Pretty simple, right? And so, again, for comments by video, this would be the table for the video view page that Cedric was talking about. Now I'm going to partition a little bit differently. I'm going to partition by video ID, which has the K after it, and then I'm going to sort by creation date and comment ID. So again, we do all this. You might notice that some data is going to get repeated here, right? Because things are denormalized, right? And as we mentioned a couple times, Cassandra uses a denormalized data model. And again, that is strictly for optimizing read performance. Right. Okay, so we can now map this out to a logical data model. Great, or excuse me, physical data model, pardon me. That was the logical data model. If we kind of go back here, what changed between these two slides? I'm going to do a visual diff. Besides the different data types here being filled in, what's different? So we lost a column here. Now, because this might be an optimization as we start to map out our types as part of the physical data model. So, we had this comment ID, but it got collapsed down to a time UUID. See, before here we had creation date and comment ID. Now suddenly it's just time UUID. Why is that? Well, because we have this optimized field type in Cassandra, a time UUID. It's a combination of a timestamp and a unique user identifier that you can put in a single field, right? So it's just a nice little optimization that's available in Cassandra. So why not use it, right? Now, do you have to? You know, if you implemented your data model like I showed here on the previous slide, would there be a problem? No, right? This is just an optimization. We're just trying to give you the feeling for things that are available to you in the Cassandra's data types that you might be able to optimize a little bit more when you're moving from the logical to the physical data model. Okay, so just summarizing again, you've got a user ID that's cast as a UUID type field. Comment ID is a time UUID, and then we combine that created at and comment ID into that one field. Video ID again, UUID, comment is text. All right, so we're pretty much there. Now it's time to write code. Optimize is an optional step. And so, if you map this out to your tables, it's pretty quick, right? You're saying basically, create table here. You've got your user ID and then your comment ID. That's your column here. If you look down in the primary key here for your first table up at the top. And then you're saying, you want it ordered by comment descending, right? So that when you read that data out, you don't need to do a sort in your application logic or your user interface tier or something like that. You don't need to pay the cost of ordering at read time. Again, once again, always storing data the way you're going to use it. We're saving it that way on disk. So it's already in time ordered format. So whether it's 3 nodes or 3,000 nodes, that is part of what helps you get all of the promises that Cassandra makes, right? And get all that value. Okay, so that's just the overall process. That's it. You start with your app workflow. You work those out. You use those to generate your pseudo queries, your pseudo tables, and then you start to kind of refine and notice that because it's a denormalized data model, you don't have joins and everything like that, the queries are actually really simple. And then you can just take that to generate your query code. Again, good rule of thumb is a query per table. So if you do one query for one table, you're going to be off to an absolutely fantastic start with your Cassandra application. All right, so let's go back to another lab. Cedric, you want to grab the screen share back for me, and let's show people how easy it is to create, read, update, and delete.
Yeah, let's do it. But you might ask the question: if there is no join, how do you do the data modeling for one-to-many or many-to-many? If you are familiar with relational data model. Well,
yep.
With what Peter just shown, a comment could be, a user can have multiple comments, a video can have multiple comments. It's many-to-many. You create X table where X is the number of queries you need. Okay, so let's go to these lab number 3, create, read, update, delete operations. So I think I can do clear here. The table are created. We can go and start inserting some data. So insert into first comment. So I'm here, step 3A, create or insert data. So here I will insert, providing the values. So very, very similar to SQL here. Just provide insert into, table name, column name, values, all the values. I will mention that UUID is a type. There is no quote around the UUID. And I will do it 3 times. So you might ask, why a UUID and not an integer, for instance? Well, let's go back to how do you want to store an integer that is unique in the table. With relational database, you are using something called auto increment. In Oracle, you are using something like sequences. You just ask the sequence, give you the next value. What do you do when you do that? You need to stop the world and ask every node, what is your latest version? Get that and work with it. So there is a lock. And with Cassandra, we hate that. So instead of that, we are using the UUID approach, where you need an identifier. You don't need to sync with anybody. Just create a UUID out of the blue, because we know that UUID are super unique. They are so long. They are probably more UUID than atom in the universe. This is where it's come from. Not to have to block multiple nodes to get that IDs. Okay, so I do have a couple of, can I select from users? Hey, no closed where, not very a good query because I'm doing a full scan of my cluster. I did not provide any partition key. So here I got it. So now if I insert into post by user, 1, 2, 3, 1, 2, 3, let's do it. So inserting into those 3 tables. So post by user, or only post by user for now, and post by room, it's coming. So same data, but inserted in the second. Here I go. So see, to copy paste, I'm using this icon over here. It will copy the cell in the clipboard, and I'm able to copy paste from one screen to another. Okay. So to insert, provide the values, you need to provide every field from the primary key, but all the others field could be let blank. Okay, adding a colon, letting a colon null in Cassandra has just no cost. On the contrary, a relational, I don't know if you have add a new colon in a relational database. Even if all the existing values should be set to null, it takes a while because each field needs to be updated. Each row, each record needs to be updated. Cassandra, it's not the case. If you do not talk about one column, it will not be used or saved on disk. Okay, so now let's read. Okay, read all the rows. Again, that's cool for development. Never do that in production. Okay, you always want to do a where clause and always provide the partition key. I will keep saying that for the next 20 minutes. And then you can go back and do something. All right, so speaking of where clause, remember it was post by user, and the schema post by user, post by user, the user ID is the partition key, so it needs to be in the where clause. Let's do it. Okay. And you can see that partition ID does not ensure unicity inside one partition. There are multiple records. You save together what you want to retrieve together. It's kind of doing the group by when you save and not when you select. Okay, so same for post by room. I select from the room, and then for a second query, I provide a room ID. Because for the second query, now room ID is my partition key. If I try to select not on the room ID, but let's say on the user ID in table 2, what will happen? User ID, I mean, why not? It does have the same data, the same record, right? So let me try that. Error. That expected. You try to select on something that is not part of the partition key. So let's imagine that your cluster have 1,000 nodes, which is not stupid. Look at the numbers on Netflix and Apple. So it will ask every single of the 1,000 nodes, do you have it? Do we have it? Do we have it? Eventually, it will be slow. And this is why you always need to provide a partition key in the where clause. Okay. All right. Here with all the data, convert post ID to a timestamp. So you can use some function to convert what you retrieve, a few function on dates, and you can use some label. So here, instead of having the post ID here, I will move that as a date. And here, so the post date is there. So whoa. So we bring an identifier and we were able to get out a date from it. And the reason is, if you look at the table schema, where is my table schema? It's a time UUID. It's an identifier that's also hold a timestamp. And this is one of the optimization that you can do at Cassandra level. Okay, so we got our few valid queries. I propose a queries that is not valid. There is a way to make it work, or at least something with non-predictable response time, but it's not recommended. So I will try not to use it in front of you. Okay, so now when it comes to update, very close to SQL. So update set, okay, command to execute, update, set what you want to update, where. And for the where clause, now you need to provide the full primary key, right? You will update one record. So here we go, updating one record, getting the updates of this record. So 111111 and post ID. So it was this guy. So second row on my screen that we updated. Okay, and okay, insert into, let's do it. And now we got a new one over here. Oh, is it a new one? Look at that. I still have 4, and before I had 4. What's the problem?
You did an update.
Did I?
Did you?
Yes, I did. In Cassandra, insert is an upsert. There is no read before write. This is one way to write super fast. It will just override what's in the database, and it does not care of what if something was there before or not. That's a default behavior. You can make sure that the record was not existing before using something called lightweight transaction or LWT, but 2 hours are not enough to cover that. But this is also one way in Cassandra to go fast. Every insert is an upsert.
It's written it's written on Cassandra's tombstone.
It is. Cassandra jokes. And removing data. Speaking of tombstone, wow, exactly. Good timing. So now, if I want to delete something from the database, I will delete from, and I will. Okay, let me copy that. When you delete, obviously now you only get 3 items. Cool. But what you need to realize then is append-only system. What Cassandra actually does was to create a new row in the table stating that, hey, this one should not be visible anymore. And this row, technical row, is called a tombstone, as Peter stated. So let's say you're running out of space in your cluster. And you say, sure, I will delete a couple of rows. It will be even worse because you will keep adding in your table new rows stating that, hey, it should be deleted, it should be deleted, it should be deleted. So there are ways to delete the records like truncates or deleting by part and then making sure that you remove the tombstone immediately. All right. So see, create, read, update, delete. But you need really to know your queries in advance to shape the tables. Okay, last 10 minutes. Let's see if you guys were very focused and listened to everything that mostly Peter said. I was just doing some exercises here. So I propose everyone to do a quiz.
What I'm taking away from all this is that inserting null values is a great best practice, right? Is that what you were saying?
Never do that. And you know.
All right. Oh, that wasn't the quiz. That wasn't the quiz. Okay.
Come on.
Right, good.
It's
All
intro to
right,
Cassandra. Don't be nice with the attendees. Be nice with the attendees.
Okay.
Okay, everybody.
Okay.
We will finish on time. So going back to menti.com, and here I'm showing again the code. It does not change, or the QR code. If you join the session in the middle and you are not already in Menti, open a new tab, go to menti.com, enter the code on the screen. The code will be the code is also in the YouTube chat for you to copy paste. And okay, so a little bit of housekeeping. YouTube can have a delay. That's how the streaming works. And the faster you answer, the more points you get, as long as the response is the good one. So when the newcomer questions show up, look at your phone first. This is where the question will show up first. Again, YouTube has a delay. So let's wait for you. So how many survivors do we have for the session? So let's see. YouTube, tell me we are about, where are you? YouTube. 70. Okay, so let's wait to have what? 50 in the game, and let's start. Okay, it's moving. 44. Yeah, I don't want to make people who stay there to the end not wait too long. So let's get running. I'm not even sure how many questions I do have for you. Okay, let's do it. Ready? Okay. 8 questions. Yeah, woo. We will be on time. I didn't expect 8 questions. Okay, let's get ready. 1 or 50. We do have the name, so 10 more seconds and it will be too late. 9, 7, 6, 5, 4, 3,
2.
Let's go. Okay, question number 1 is how many master nodes does Cassandra cluster need? At least 3 per cluster, 3 per DC, enough to maintain consistency. Not a single one. Cassandra is decentralized. Hey, so indeed, most of you I did correctly. So Cassandra is a masterless system, no master, decentralized, so no need for any master. So looking at the leaderboard, who was the fastest among you? I want to see your names.
Ooh. All right, look, Mark R is looking like he's taking the lead. Pranodi's coming in on a hot second.
Fastest data, but look at that. Oh, 3 points. That's just nothing. Yeah.
Wow.
30 milliseconds. Come on. Nothing. Okay. 7 more questions to go. Question 2. Answer fast to get the most points. How data is being distributed? All data is replicated to each server by partition, range of partition per node, with address locators using post mail. Man, what's the point to replicate your data everywhere? Okay.
All right.
Yeah, indeed, you shard partition your data and save a range of partition per node.
Excellent.
Okay, looking at the label.
Yeah, it's like people were paying attention. This is great. Vote GOAT is, I'm pulling for Vote GOAT personally.
Oh yeah, vote.
Oh, there we go. Vote GOAT is in the top.
Oh yeah.
All right. Excellent username. You are to be commended, sir. Or madam.
Okay. I will vote for the people who ask the most questions in the YouTube chat. Okay, question number 3. Are you ready? Let's go. Which replication factor is recommended? Oh, this one is a speed question. 1.5, 3, 15, 42. And I don't know how you can be half replicated. Just one arm, or I don't know. All right, it's 3 indeed.
Wow.
Oh, everybody was correct. 2 easy question.
Consistency level was all on that one.
Okay, so Mark was the fastest for the second time, but enough to be on the podium. But VoteGoat lead the way. Question 4. What is ASTRA-DB? That's a good question. What is ASTRA-DB? It's a gateway to the star. It's a local in-memory version of Cassandra. It's Cassandra as a service in the cloud. It's a development tool. In France, it's a butter brand.
Really? Interesting.
Yeah, it is also a movie, No, Ad Astra is the movie. Yeah,
Oh, yeah.
It's Cassandra as a service in the cloud. So look at
literally the worst Brad Pitt movie ever made. Yes, that one. That's right.
Okay, VoteGoat, Joey, Igjo, Pranoti. All right. But France was the fastest this time. Okay, question 5. Everybody's ready? Let's go. What is a primary key? Same as partition key. It's the main house key. Does not apply to NoSQL databases. Uniquely identify a row. It's a column in the partition key.
Ooh, you had a couple of false positives
in
here. This is a little harder. All right, this is good.
Yeah, indeed. Primary key is really there to identify the unicity of a row, a record, and it's composed with both partition key and clustering column. But we did not really cover today the clustering column, so yeah, it was not that hard. Okay, vote elements oh wow. Yeah, seems like it was tricky. Not everyone got it correct. Oh, seems like VoteGoat is definitively your champion, Peter. Maybe it's you. Who knows?
Yeah.
All right, question 6. 3 more questions to go. What is the partition key now? Oh. A consecutive number applied to each new record, a designated field in your table to partition your data, an optional table field with optional partitioning, the key to partition the reality from the next. Oh, wow. Okay, indeed, it was not that hard. A bit of text to read, but you can easily remove a couple of options to keep the latest.
Right. I'm just
vote.
I'm just gonna go on record and say that VoteGoat is not me, and Ion or Elon or Ion already called it out. So I don't know. Maybe he gave himself away there. Could be him.
Okay.
Joey with a respectable performance and Hemonth as well. All right, guys, ladies.
Indeed.
Good.
Okay, 2 questions. Let's try to finish almost on time. Executing select without the partition key is bad. Now, the recommended way to retrieve data, the right way if the data was inserted without the partition key, a way to full scan master, illegal and punishable by law. I vote for number 4,
I know.
even if it's...
Yeah, seriously, I know.
It cannot really be correct.
All right, and the answer is avoid the full cluster scan at all costs.
Indeed. Joey Burba. So does that mean that Iron Olau was VoteGoat? Who knows? It just stating that he failed on purpose.
Uh-oh. Aaron.
Maybe yes, maybe not. Okay, last question, people. Okay, and then wrap up, and yeah, we can all have a drink. In the data modeling framework, we start modeling with the conceptual data model and application workflow, with the physical data model, with the logical data model, with copy-paste from Stack Overflow.
Clearly, the right answer is copy-paste from Stack Overflow.
Especially for the design, right? Indeed, both are needed, conceptual data model and the application workflow. Application workflow means your queries. Okay, final leaderboard. Who was the fastest among you?
Drum roll, please.
And
we need some Jeopardy music, by the way, for during these.
I think Stefano is playing music for us right now.
Oh, cool.
Okay,
right.
So 3 winners. So take a screenshot of your screen right now. And you will send an email that I will show you in a minute to jadfryer@datastacks.com to reclaim your prize. Okay, so the 3 winners. And now that you have done your screenshot, I leave open a survey for you, help us to improve. What should we do differently? And we will review your answer, after the session. So let's finish on time. So what's next? We did the game. So send the email, Harvey. So the session is recorded, will be available at same link, so you can catch up and get the email address for the winners, easy. So the homeworks, !homeworks. It was in the README, remember, is here, homeworks. Here at the beginning, there is a Google form. So homeworks, here. Submit your Google form here. A couple of questions, a screenshot to share, just proving, and you are okay to get your badge. If you still have questions after the session, we will be on Discord or all week long answering your questions. So !Discord. If you are with us up to the end, so hope you enjoy the format, the energy. So please don't hesitate to subscribe to the YouTube channel. This is what keeps making us coming back every week. If you want to know what's coming in 2 weeks, datastacks.com/workshops. And I think in 2 weeks, it will be build a clone of Netflix. So this one at the top right-hand corner, build your own Netflix clone using some JavaScript code. So, if you're interested, make sure to register for the one in 2 weeks. And with that, I think I'm done. Any final comment, Mr. Peter?
I'm just amazed we hit this like 3 minutes. That's only 3 minutes past time. That's pretty good.
We are
all right.
Professional,
Yeah, it's almost like we've done this before. Thank you everyone so much for joining us. And yeah, like Cedric was saying, I think there's lots more for you on the YouTube channel, not just more workshops. There's tons of other learning available for you if you want to dive deeper, self-paced on your own. There's a wealth of information, DataStax Academy courses, all kinds of good stuff. So you want to continue to sharpen your skills. Sure, come back for workshops, but there's also plenty of self-paced stuff on the YouTube channel. And tell us what you want to see. Tell us what you want to see on workshops. Tell us what you want to see in the YouTube channel. Join the Discord and tell us what you want, and we'll make it. That's what we do.
Exactly. And until then. Good night, good evening, everyone, and see you all in 2 weeks. Bye.
And as always, don't forget to click that subscribe button and ring that bell to get notifications for all of our future upcoming workshops.
Being gifted with powers from the goddess of Cassandra. who grew those powers until she could multiply at will, move with limitless speed, and unmask hidden knowledge. With those powers, she was able to fully understand the connectedness of the world. What she saw was a world in need of understanding. From that day forward, she sought to bestow her powers on all who came into contact with her, empowering them to achieve wondrous feats.